Hi Wildcats, this is an overview of some example problems from Unit 9, Focus Question 2, Work and Energy. And our goal in these is to see how mathematically we can use the relationship between work and the different types of energy to describe the different characteristics of an object. So in our first problem here, a cat pushes a 1.2 kilogram vase off a shelf that is 2 meters above the ground. And we need to know how much kinetic energy the vase has when it hits the ground. So we've written down what we know. In order for us to get kinetic energy, with that equation is 1/2 mv squared. So they give us mass, but we don't have velocity. So really we need the velocity of the vase when it hits the ground. So if we think about this with the vase being here and it travels down 2 meters, we are looking for its velocity here at the end. We know that if it's sitting on the vase, its initial velocity would be 0 meters per second. So we need to start by doing some kinematics here. If we recall our kinematics equations, we know that V final squared is equal to V initial squared plus 2 times acceleration times the distance that an object travels. So the initial is 0, so that can go away. So V final squared is just 2AD. So we put in 2. This is on Earth, we're going to assume. So acceleration due to gravity is 9.81 meters per second squared. And then that's down, so we would put negative. And then its displacement is 2 meters down, so minus 2 meters as well. So V final squared is going to be equal to, if we do that math, it works out to be about 39.2 meters per second. So we could square root this, but if we look at our equation for kinetic energy, it's 1/2 mv squared. So I actually need V final squared here. So if I square rooted it here to get the answer, to get V final itself, then I would just have to square it over here. So I can just actually leave and use 39.2 in my equation here. So now solving for kinetic energy of the vase when it hits the floor, it's going to be 1/2 times the mass, which is 1.2 kilograms, times V final squared, which is 39.2 meters per second. And so I find out that the vase has a kinetic energy of about 23.5 joules when it hits the ground. Something that the text didn't talk about necessarily is energy is a scalar. It doesn't have direction. Energy is just a quantity that describes how much energy an object has. So if we were to ever get a negative value here, that wouldn't actually make any sense. So it's good that we got a positive value here because energy is a scalar itself. So let's move on to a potential energy problem. Here we have a ball, let's say it's Wanda Jr., because it's only 2 kilograms. It is attached to a ceiling. It says that the ball is 1 meter from the ceiling and that the room is 3 meters high. So that tells me that this ball must have a height off the ground of 2 meters. So they want me to figure out how much gravitational potential energy it has relative to the floor. So I need mass times acceleration due to gravity times height. So I actually have all those values, so I can just get to work on this. Its mass is 2 kilograms. Acceleration due to gravity is negative 9.81 meters per second squared. And its height off the floor, it would be going down 2 meters. So its gravitational potential energy would be, if I multiply all those together, I get 39.2 joules. Okay, so we're just plugging in our values. The potential energy gravitationally an object has is its mass times acceleration due to gravity times height. Using work kinetic energy theorem, I can also describe the properties of an object. So in this problem, a student wearing frictionless skates, so that's good. We're not going to have to do any net force stuff because it's frictionless. On a horizontal surface is pushed by a friend with a constant force of 45 newtons. How far must the student be pushed? So we're looking for its distance. Starting from rest, so V initial is 0, so that they have a final kinetic energy of 352 joules. So this is the work kinetic energy theorem. So I know that the net work done on an object is equal to its change in kinetic energy. Or I could say, write this out long form. I know work is equal to force times distance. And I'm looking for distance, so that's good. Change in kinetic energy is 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. So velocity initial is 0 because it starts at rest. So this whole part of my equation goes away. So if I'm looking for distance, I can just divide both sides by force here. And displacement is going to equal 1/2 mass velocity final squared divided by force. Well, I don't have velocity, and I actually don't even need to find it, because really this 1/2 mass velocity squared is the same as saying kinetic energy final. So they tell me the kinetic energy final. The kinetic energy final is 352 joules. And so I just divide that by the force upon it. So it would be 352 joules divided by the force that's applied to it, which is 45 newtons. And I would see that this student, in order to have that 352 joules of energy, would have to travel about 7.82 meters. So the key to this problem is understanding that work is equal to change in kinetic energy. Work is also equal to force times distance, and then change in kinetic energy is final kinetic energy minus initial kinetic energy. Since the object had no velocity at the beginning, it had no initial kinetic energy. So our last one here, we have a 1,500 kilogram car traveling down the road with an initial velocity of 11 meters per second when the driver takes their foot off the gas. So with their foot off the gas, we can assume the only force acting on it is friction. It takes the car 104 meters to come to a stop, so its final velocity would be 0. What is the force of friction between the road and the tires? So again, we're going to want to use the work kinetic energy theorem. Work is equal to kinetic energy final minus kinetic energy initial. So work here, since we're looking for force, the force of friction is what's doing the work slowing the car down. So we really would write this as the force of friction times the distance is equal to kinetic energy final minus kinetic energy initial. Well, since the final velocity is 0, it has no kinetic energy. So really it's just the kinetic energy initial, the opposite of kinetic energy initial. So I'll write that out long form, 1/2 mv initial squared. And since I'm looking for force, do my algebra first. I'm going to divide both sides by distance, so that cancels out. And so I'll get the force of friction is equal to negative 1/2 mass, which is 1,500 kilograms, times its initial velocity, 11 meters per second squared, all divided by the distance that it takes to stop, which is 104 meters. And so when I get this force of friction, I get a negative, if you multiply that out, I'm still going to have the negative, I get negative 873 newtons. And so if we stop and think about this for a second, that makes sense. So the velocity is positive 11 meters per second. So that means my object is traveling with a velocity initially to the right. So we know the force of friction is always opposite the direction of motion. So force of friction would be to the left, which means it's going to have a negative value. So it's good. It tells me that I probably did this right, that I ended up with a negative 873 newtons. So I hope that helps. If you have questions, there are other practice problems